A record on a record player spins at 45 RPM. Two small 30 kilogram balls of clay are dropped on the record and hit it simultaneously at the edge of the record and at opposite ends from one another. Okay, so let's just try to draw what's happening. So here's my record. Okay, it's just a disc. And I've got two pieces of clay, one here and one here. And they're both dropped at the same time, so they land on the edge of that record. Okay, so I'm trying to draw the record in 3D. It's actually coming out of the page. Treat the record as a disc with a radius of 12 centimeters and a mass of 455 grams. And the clay balls, we're just treating them as particles, which makes sense because they're very small compared to everything else. What's the record's angular velocity just after the clay balls hit it? All right, so when we look at this system with the clay balls and the record, there are no external forces that are acting on the system to make it rotate. Okay, it's just what's in the system. The record itself is already rotating, but there's no external forces that will make it speed up or slow down in a rotational sense. And so there's no net torque acting on the system, which means the angular momentum is conserved. So the total angular momentum before the collision, which means before the clay touches the record, is equal to the total angular momentum afterwards. Okay, so we have angular momentum of two different things. We have the two clay balls and we have the record. Okay, initially, do the clay balls have any sort of angular momentum? Okay, let's think about that. So the clay balls, are they causing anything to rotate when they land on the record? Are they causing it, are they making it spin in one direction or another? Or in other words, do they apply a torque? Is there a torque applied? Okay. So if we think of this, it's coming, the record is in 3D. So it's a little bit hard to draw what this looks like, but if a ball of clay drops on top of a record, okay, on top of a disc, it's not making the disc rotate in any way, right? There's no torque acting on the disc. So those balls of clay do not have angular momentum initially. So we're really just talking about the angular momentum of the disc itself, so the record. Okay, so this is going to be the angular momentum of the record. The formula for angular momentum is I times omega of the record initially is equal to the angular momentum of them after the collision. Well, now the clay balls are touching the actual record, so they're all spinning together. Now they are spinning because they're on the record. So it would be the I of the record plus the I of, I'm just going to put two clay balls like this because there's two of them, times the omega final. Okay, we're looking for that omega final. So we have to think about what are we putting in for I. So I for the record is a disk. If we look at the table that has all the moment of inertias of different shapes, the moment of inertia of a disk is just 1/2 mass of the record, r of the record squared, times omega of the record initially is equal to I of the record, same thing, 1/2 m r the record squared, plus the moment of inertia of those two balls of clay. Well, we have two balls of clay, we're treating them as particles. The moment of inertia of a particle is just mr squared, but we have two of them, so it'll be 2 mass of one of those balls of clay, r squared. Okay, the r is the distance from where the clay is to where the axis of rotation is, which is still the radius of that record. So it's the same r in every case, times omega final. So we can rearrange, solve for omega final, 1/2 mass of the record, radius of the record squared, omega of the record initially over 1/2 mass of the record, radius of the record squared, plus 2 mass of the clay. So there's two of them, that's why there's a 2 there. There's 2 masses of the clay times r squared. And now let's think about what we're plugging in. So the only thing we don't know right away is this omega initial is not in the correct unit, so let's just convert. Omega initial is 45 revolutions per minute. We'll change revolutions to radians. 2 pi radians is 1 revolution. We'll change minutes to seconds. 1 minute is 60 seconds. And I'm just going to type this up. And I get 3 over 2 pi. Okay, so now I should be able to plug everything in. 1/2 mass of the record. They tell us the mass of the record is 455 grams. I'm just changing it to kilograms. Radius of the record is 12 centimeters. Again, we need to change it to SI units, so 0.12 meters squared. Omega of the record initially was 3 over 2 pi, what we just calculated on the side, over 1/2. Mass of the record still 0. I typed that wrong, didn't I? 455 grams. So it should be 0.455. And on the bottom again, 0.455. The radius of the record is 0.12 squared plus 2 times the mass of that clay. The clay balls are 30 grams, so we just need to change that to kilograms, 0.03. The radius is the distance between where the ball of clay lands and the axis of rotation, so it's still the radius of that record, which is still 0.12, and it's all squared. So I'm just going to type all of that in. And I get 3.73 radians per second. Alright, I can look at the significant figures in the question. I have 3 significant figures, 3 significant figures, 3, and 3, so my answer should have 3. So I'm all good. Alright, I hope that helped. Thanks for watching.